Hey everyone, this is Mohammed Nadeem and welcome to my YouTube channel. Today we will demonstrate about the mutual inductance. So for that, we will use this device which is the galvanometer used for detection of the current. This is the transformer and this is the AC supply. Before starting the demonstration, we will have to cover the theory behind it. So for that, we have this coil, and this coil is made by the copper laminated wire which is 0.2 mm in diameter, and here is about 110 number of turns present in this coil. And similarly we have this is the another coil, and as we know that if we provide the potential difference to this conductor here, to these terminals of the coil, if we provide the potential difference, the electric field will develop inside this conductor. Due to that electric field, the force F will be exerted on each and every free electron present inside this conductor, due to which that free electron will start motion. Due to their motion, the change in electric field will develop the magnetic field around this conductor, and here is that same conductor, and we form the coil from that. So here that magnetic field from each conductor will be added off, and due to that the one side of this coil will be act as a north and the other side of this coil will be act as a south, and now this coil will behave as a permanent magnet. Okay, so we have this scenario, and here due to this battery, this will behave as a permanent magnet. And now we have this is the another coil, and if we bring this other coil near and away to this coil which is actually a permanent magnet, so if we bring this coil near and away to this permanent magnet, the change in magnetic flux of this primary coil will be occur. Due to change in magnetic flux according to Faraday law of electromagnetic induction, the EMF will be induced in this secondary coil, and that EMF which is produced due to the mutual flux we called as a mutually induced EMF. That same case present inside this transformer. So in this transformer, we have two coils. One is this coil with the blue color, and here in this coil we have the number of turns, and that number of turns is larger than this coil. So this is the white color is also the another coil with the small number of the turns. These two wires are connected with this coil, and these two red wires are connected with this coil, and the coil with these red wires have large number of the turns as compared to this. Okay, so here the number of turns is more, and here the number of the turns is less. If we provide the potential difference to this red color wires, so the magnetic field will be developed around this coil, and that magnetic field will interact with this coil, and due to their interaction, due to the change in magnetic field of the primary coil and their interaction with the secondary coil, an EMF will be induced, and that induced EMF will be shown on this device. Now we will connect this terminal with the AC source. So this is the AC source, and here before that I'm going to connect this secondary coil with the galvanometer, and this is the one probe and this is the other probe of this galvanometer, and I'm going to connect this one probe of the galvanometer with this one wire of this secondary coil. Okay, and similarly I'm going to connect this second terminal of the galvanometer with the second wire of the secondary coil. So I have connected that. Okay. So now I'm going to connect these two wires of the primary coils with the AC supply. Okay. So here I'm going to connect these. Okay. Okay. Is if I connect this, so here on this galvanometer, this needle of the galvanometer start vibration. So it is vibrating, and their vibration is about uh, 50 times in a second, mean that its frequency is 50 hertz. In most countries, the frequency of alternating current is about 50 hertz, mean that 50 times their polarity will be changed. Okay, so here it is vibrating about 50 times in a second. And here, if I provide the AC source, so here the polarity of this AC source is changing. So here, due to the change in the polarity of this AC source, the change in the poles of this, the poles of the magnetic field of this primary coil will also occur. So they change in the poles of the magnetic field produced from this primary coil, uh, we call as a change in a flux. So, according to Faraday law of electromagnetic induction, if there is a change in magnetic flux, okay, it will induce the EMF. Okay, so that change in magnetic flux is linking with this coil, and due to that change in magnetic flux, the EMF will be induced in this secondary coil, and here we connect that secondary coil with this galvanometer, and due to which this galvanometer show us deflection. So here the polarity is changing 50 times in a second, due to which the magnetic field of this primary coil changes 50 times in a second. Their direction is changing 50 times in a second. So then, according to Lenz's law, the induced EMF will also change its polarity 50 times in a second. So here, the terminal of this galvanometer vibrating 50 times in a second. So actually, this is vibrating. And now I'm going to disconnect the AC source here. So here I'm going to disconnect this. Now this needle is not vibrating, and again I'm going to connect this, then it will start vibration. So focus on the needle of this galvanometer. Okay, so here I'm going to again connect this. So here I connected this. So it again start vibration. Okay, so if I disconnect this, then it stop the vibration, and again I connect this, and again it start vibration. Okay, so this is the theory behind the mutual inductance. The change in magnetic flux of this primary coil, the change in magnetic flux of this primary coil is linking with the secondary coil, and due to it the EMF is induced in this secondary coil. Okay, and that EMF is shown by the galvanometer there. Okay, so now what will happen if we provide the DC source here instead of this AC? So this is actually a DC source. This we call a battery, and the one side of this battery is the negative and the other side of this battery is the positive, and forever this side will be the negative and this side will be the positive, and it will not change their polarity. Okay, so here I'm going to connect this DC source. So if I connect the DC source during their connection, okay, during the time we connect this, the galvanometer show the deflection, but again it come to its zero position. Okay, and if I disconnect this, then again this galvanometer show deflection, but it will come again it's against to its zero position. So here this is in zero position. Now I am going to connect the DC source. Okay, so during their connection, so this is the connection time, this show the deflection, but again it become zero. Okay, now if I'm going to disconnect this, then again it show deflection, but again it comes to its zero position. So what is the physics behind that? Okay, so the physics behind that is this. So here if I connect this primary coil with this DC source, okay, at that small interval, the magnetic field will be produced around this solenoid, okay, and that magnetic field will be changes for that small interval, and that change in magnetic field will interact with this secondary coil, and according to Faraday law of electromagnetic induction, the change in the magnetic field will induce EMF. Okay, so therefore, for that small interval, this galvanometer will show the deflection. But again, it come to its zero position even if I connect this DC source with this, and there the galvanometer show us the zero deflection. This zero deflection is because when we connect this, okay, so the now the polarity of this DC source is not changing, due to which the magnetic field is producing, but their magnetic field do not change, mean the change in magnetic field is not occurring. So due to which the change in magnetic flux is zero, so due to which the EMF induced in the secondary coil is zero. Okay, so here still the magnetic field is present, but the change in magnetic field is absent, so therefore it show the zero deflection. But if I disconnect this, during that time it show deflection. So during that time, the magnetic field produced from this primary coil is reducing for that small interval, and it going to the zero. It going to the zero magnetic flux. So therefore, for that small interval, it show as the deflection. Okay. So here was the demonstration of the mutual inductance. Okay, so if I connect this again with this AC source, okay, so I'm going to connect this. So uh, if we provide the AC source, the magnetic flux which is produced from this primary coil, and that is interact with this secondary coil, is called the mutual flux. Okay, and the properties of these two coils to produce the magnetic the flux, the change in magnetic flux in the primary coil, and that is linked with the secondary coil. This properties of these two coils is called the mutual inductance, and this phenomena of the mutual inductance is called the mutual induction. Mutual inductance, which is represented by this capital M. Okay, so the EMF, the EMF produce the EMF induced in the secondary coil due to the change in magnetic flux of the primary coil is directly proportional to uh, the change in the current, okay, the change in the direction or the magnitude of the currents in time del t. Okay, so here the EMF induced in the secondary coil is directly proportional to the change in the current in the primary coil at time del t. Okay, so as we know that instead of this proportionality sign, we will put is equal to an constant. So this electromotive force is equal to a constant, okay, and del I by del t. And instead of this constant, we will put M, and which is called the mutual inductance. M, which is called the mutual inductance, and del I by del t. This is the expression for the EMF induced in this secondary coil, and according to the Lenz's law, the EMF induced in this secondary coil will always oppose the change in the magnetic flux of the primary coil. So here for that we will put the negative sign in this, and this is the equation 1. And here this M is called the mutual inductance, mutual uh, inductance, and this mutual inductance depend upon the shape and position of the coil, position of uh, coils. Okay, so here the shape of the coil. So this coil will have different mutual inductance, and this if we change their shape, then it will have different the mutual inductance. So this mutual inductance depend upon the shape, and the other factors of the mutual inductance is the position of the coil. So if here these two coils are parallel to each other, so if we put these coil at some angle to each other, then their mutual inductance will be different. So here the mutual inductance depend upon the position of the coils. So this is the equation 1. And now according to, so here the unit. So what is the unit of the mutual inductance? The unit of the mutual inductance is Henry. Henry. Henry is the unit of the mutual inductance, and which is represented by H. And from this equation, the EMF, from this equation, M is equal to EMF, okay, divided by del I by del T. Del I by del T, which is equal to EMF multiply del T by del I. Okay, so here if we put this electromotive force, so here M, so here if we put this electromotive force as 1 volt, okay, and this change in time is 1 second, and this current is 1 ampere, then in this case the mutual inductance will be 1 Henry. This is the unit of the mutual inductance. Okay, so now according to the Faraday law of electromagnetic induction, the the EMF induced is equal to minus n del phi by del t, and this is the equation 2. Now compare equation 1 and equation 2. So this is the equation 1 and this is equation 2. Compare equation 1 and equation 2. So the left side of equation 1 is equal to the left side of equation 2. So therefore the right side will be equal. So here the right side of equation 1 is minus m del I by del t, and the right side of equation 2 is minus n del phi by del t. So here this del by del t will be cancelled. This positive and this negative will be cancelled. So in the left side, the m, the mutual inductance, okay, and this I will be remain is equal to in that side this n and this phi has remained. Okay, so from here the m will be equal to, we will divide this side with the I and this side with the I, and these I and I will be cancel out. So this equation will become m is equal to n phi by I. Okay, so this is the final equation for the mutual inductance.